Good afternoon. My name is Amit Mishra, and I am the chair of the Material Science and Engineering Department of the College of Engineering. It's my great pleasure to welcome all of you to Lawrence H. Van Vlack Lectureship and MSc presented by Nobel laureate Professor Stan Whittingham. I would like to thank the endowment and support from the Van Vlack family. Professor Larry Van Vlack's son, Bruce, is in the audience today. Also, I would like to thank Katsuya Thornton, the current Lawrence H. and Francis E. Van Vlack Professor of Material Science and Engineering, for organizing the lectureship. Professor Larry Van Vlack, for those of you who don't know him, in 1959, he published the first edition of a textbook titled Elements of Material Science, an introductory text for engineering students that set the foundation for undergraduate curriculum and independent material science and engineering academic departments all over the world. In 1976, Dr. Stan Whittingham, working at Exxon Corporate Research Labs at the time, published a single author paper in Science that described the electrochemical reactions of layered titanium disulfide with lithium, giving the intercalation compound titanium-lithium disulfide as the basis for a new battery system. The intercalation reaction was shown to occur very rapidly and in a highly reversible manner at ambient temperatures as a result of structural retention. Since then, lithium-ion batteries were commercialized initially for portable electronics and are now ubiquitous in daily life in increasing diverse applications, including electric cars, power tools, medical devices, smartwatches, drones, satellites, and utility-scale storage. Currently, the global lithium-ion battery market is valued at over $40 billion and is expected to grow more than $90 billion by end of this decade. This is one of the many transformative impacts in modern society originating from fundamental scientific research and education in chemistry and material science, starting with undergraduate courses in thermodynamics, kinetics, and structures of solids, following the vision that Professor Van Vlack had in 1950s. Last fall, we enjoyed Professor Stan Whittingham's online seminar, and we are very pleased to have him visit us in person for a public lecture. I now invite Professor Alec Gallimore, Dean of Engineering, to make remarks and introduce today's lecture. Please join me in welcoming Professor Alec Gallimore.
Good afternoon. Dr. M. Stanley Whittingham received the Nobel Prize in Chemistry in 2019 along with John Goodenough and Akira Yoshino for the development of lithium-ion batteries. As the Nobel News release noted, this lightweight, rechargeable, and powerful battery is now used in everything from mobile phones to laptops and electric vehicles. It can also store significant amounts of energy from solar and wind power, making possible a fossil fuel-free society. Dr. Whittingham has been active in this area since the early 1970s, when he won the Young Author Award of the Electrochemical Society based on postdoctoral studies at Stanford. In 2018, he was elected a member of the National Academy of Engineering, among the highest professional distinctions accorded to an engineer. And last year, he was elected a Fellow of the Royal Society, which is composed of the most eminent scientists, engineers, and technologists from the United Kingdom and the Commonwealth. Dr. Whittingham earned his bachelor's, master's, and doctoral degrees from Oxford University. He is a distinguished professor of chemistry and of material science and engineering at Binghamton University, which is part of the State University of New York system, where he helped to establish the Material Science and Engineering graduate program. Today, he will discuss overcoming climate change, the critical role and challenges of energy storage. Please welcome the 2019 Nobel laureate in chemistry, Dr. M. Stanley Whittingham.
Thank you very much, all of you, and thank you for coming, and thank you for the Van Vlack family for enabling this lecture. And I'd like to thank all the university for the invitation. This has been delayed 2 years because of COVID, but I'm happy to be here now. I gave a technical talk, I think, last fall. So what I want to talk about is really the issue of climate change, then switching into how energy storage can solve the problems. But I also want for the more junior folks in the audience to show how things in your career can really determine your whole life. So within the last 12 months, there's been these various issues throughout North America and South America. And I'll show you just a few examples here. This is Germany. This is Kentucky. If you've been to Lake Louise, you'll notice that the Victoria Glacier has essentially disappeared. We used to go there every 2 or 3 years. And this whole valley was full of the glacier 20 years ago. So this is retreating at a very high speed. Then we also have these fires. This is one just outside of Santiago, Chile. And this is near Boulder, Colorado. So all these have been blamed on climate change. And not just climate warming. I think of climate change as really total messing up with getting extremes at both ends. So hotter, colder, and wetter and drier. So let me just talk a little bit about disruption. If we look back in our lives, some of you here will remember the time when there were no computers, no iPhones, no laptops, and our lives have really been changed since those devices have come on board, and they're all enabled by lithium-ion batteries. We can now communicate instantly around the world, and parts of the third world countries will never have landlines because now they can jump straight from nothing to wireless technology. So I want to really mention a key thing here that maybe some people won't be happy with, but we have to adapt to live with climate change. We're not going to roll it back 50 years. What we can do is hold it where it is now and make sure it does not get any worse. If I stand in the middle, maybe I can see a little bit better. What we have to do is really get off fossil fuels and in particular get off coal. And I'm very happy to say that New York State now does not generate a single kilowatt hour of electricity using coal. They've eliminated coal altogether. The rest of the country needs to do that, but if we're going to go to renewables, solar and wind, the sun shines when it wants to, the wind blows when it wants to, and the wind is strongest in the middle of the night when we don't need that energy. So what we need to do is have storage so we can shift the energy from when we generate it to when we want to use it. And the issue there is finding a, shall we say, a financially effective way of doing it. Batteries is one way, but there are several other ways. Lithium batteries have the big advantage. You can go from milliwatt hours, such as you might have on a smartwatch, to gigawatt hours, and I'll show you a facility in California in a moment. Clearly, a big polluter are internal combustion engines, and parts of the world and parts of America are going to go faster to electric vehicles than other parts. I think you're going to see major cities, and by major cities, I'm talking about major, what we call resort cities, San Francisco, Paris, London, Sydney, Australia, probably going to clean electric vehicles before anybody else, because that's what the tourists want, and that's what looks best. So I think New York's going to be doing that. They've mandated it. I think London's now mandated no more internal combustion engines in about 5 years' time. So we're switching over to that. The other big issue, we want a cleaner, more resilient electrical grid, and we can do that with storage. And in particular, if you have power outages, then if you've got storage in your house, you can solve that problem. If you've got storage in your neighborhood, you can solve that problem. And something I'll talk about a little bit later, the goal is to have what we call the million-mile battery in your vehicles. If it can last 1 million miles, you're not going to drive that far, but it means your car can be attached to the grid at all times when it's not actually moving. So you can take power into your car, take it out, and your local utility will pay you to do that. So that'll smooth the grid without having to use dirty power sources that maybe operate only 5 or 10% of the year. And that's the issue today. So what I want to do is spend just a moment, and I'm sure all the senior folks can answer this, but ask some of the more junior folks in the audience, what got you interested in science? Was it a high school teacher, a teacher here at the University of Michigan, but there was somebody who got you hooked on science or hooked on engineering, or if you're in the humanities, hooked on one of the humanities? And I want to discuss briefly my career because I really got hooked on science by a high school teacher, Major Lamb, who taught chemistry, and a physics teacher called Squibs Bowman. They were so excited about the sciences themselves, they got it into their students at that time. And then when I went to Oxford, I had Peter Dickens as my tutor. For those of you who don't understand the Oxford system, basically you go to lectures if you feel like it, but each week you have to write a 20 to 30 page paper. You take that to your tutor, and then you discuss it with him, or her these days. But the key thing is they will question you on it. They will not give you the answer. So they'll keep plugging away until you get the answer. So you learn there really how to think, how to understand things, and to present yourself. And Peter was outstanding at that. So I did my, what we call Part 2 in chemistry at Oxford. You had to do 3 years of coursework, then 1 year of research for your bachelor's degree. For the older members in the audience, they'll remember there's something called Sputnik. The Russians put up their satellite, and the US had nothing at that time. So that's the real first thrust of when money flowed into science, and in particular into the material sciences. They felt that was critical. So it was the US Air Force through their Office of Research in London that supported my bachelor's degree and several of the faculty groups at Oxford at that time. Then for my PhD, I had a, shall we say, strike of fortune. I got a 3-year fellowship from the Gas Council of England. They're the ones who controlled gas at that time. It was nationalized. I got the award in, I think, June. In August, they struck natural gas in the North Sea. And they said, we're not interested in what you're doing anymore. Do whatever you want for the next 3 years. We just want a copy of the thesis at the end. We don't want any reports, nothing. So that's the ideal situation for a graduate student. You've got your freedom to do what you want to do. Then I went to Stanford University, partly because that was the norm at that time, but also because the sun shines in California. And I went to Bob Huggins' group, and I was the second of about, in the end, 10 PhD students from Oxford who went to Stanford, almost one every 2 years for the next 20 years. And there I got to study a range of materials, but specifically I got to study beta alumina. That's the structure I show you in the middle here. And Ron Radzilowski, I think, is in the audience. He's one of the few people still around that worked on beta alumina in those heydays from about 1967 to about 1975, where this compound was exciting because ions moved as fast as in that solid as in liquid solutions. So there was a huge interest, and Ford was going to make sodium sulfur batteries at that time. But then in 1972, I went off to industry, and industry then was not the same as it is now. All the major corporations had what they call corporate research labs, which were really planning out what's going to be important to us in 10 years' time, not just tomorrow. So Exxon had set up a corporate lab, and our charge was to work on energy issues, but not petroleum and not chemicals. So I started working on superconductors, and whilst trying to make a new superconductor, we saw that a lot of energy was evolved, and we said, hey, we can store energy using these, what we call then intercalation reactions, and I'll talk about what those are in a moment. Made that discovery, Then the corporate folks said, you better go and explain what you've done to the committee of the Exxon board. I went off to New York City, gave a 10-minute talk. I think they call it an elevator speech these days. And George Piercy was chair of that committee. He was a PhD from Minnesota. Within a week, they said, we're going to build a development team and hire a manufacturing team. So they treated research really like drilling an oil well. Some will work, the majority won't work, but let's invest in it and see what happens. So from that point, Exxon was interested in electric vehicles. Then in 1988, I decided I wanted youth in my group. So the big advantage of academia over industry is you get a new group of young blood every year into academia. It keeps you young as well. So that drove me back, and I've been a manager in industry. I was, I think, 4 or 5 years doing research at Binghamton before. They said, oh, we need you to be VPR for a year or two. So I was vice president of research for the next 5 years. And those are exciting times because at Binghamton, the VPR had all the indirect funds. So you could direct where the research was going to and encourage them. And I put plans in place so faculty got some of the money back in their own pockets, which was very effective. So let's start at the beginning. At Exxon, this was me a few decades ago. These are the single crystals we use for making batteries. And I'll really address this a little bit later. In the early days of batteries, you wanted small surface areas, nice big single crystals so you wouldn't get side reactions. And Sony did the same thing when they built the first lithium-ion batteries. This is the original patent that Exxon put on the board for me last year. And these are 2 of the first batteries that Exxon actually made. So this is a paperweight. Here's the battery. Here's a little solar cell and the clock. This particular one I have at my home. It is still working. So a well-made lithium battery will last for a long time. The one beneath it is one we built for electric vehicles. It's about 6 inches by 4 inches by an inch thick. And this was used in the EV show in Chicago. So they were serious about it at that time. They really wanted to get into the business. And if you want to see those batteries, you can find 2 of them. They're in the museum in Stockholm now, these 2 here, little ones. We managed to find those in the basement and put them into Stockholm. And this is the sales brochure for the lithium batteries Exxon was making. So we went from that. This is today. So you can see the difference. Little 2-wheelers, 16-wheelers, garbage truck, and here's a couple of buses. These are made in Binghamton, and the forklift truck also made in Binghamton, plus a very nice BMW electric vehicle. So we went from almost nothing back in the 70s to really dominating the modern electric vehicle with lithium-ion batteries. And Exxon got out of the business for a number of reasons. One, they were too early. One, the business wasn't big enough, so they licensed it to the Japanese. And also what most people don't realize, the federal government did not want them getting into the business. They were dominant in the oil and didn't want them to be dominant in another area. So just to show you electric vehicles, the sales are increasing rapidly. This is the only one that's projected, and clearly they're going to meet the targets, and it's going to keep going up over the years. So they're really starting to sell. They're selling extremely rapidly in Europe, obviously in China, and will catch up eventually. Another area where lithium-ion batteries are used is on the International Space Station. So 2 of the physicists and I, whilst in Stockholm, we talked live to these 2 astronauts. The lady is from the state of Maine. Her mother is Swedish. The fellow is from Italy. And they're just finished replacing all the metal hydride batteries on the International Space Station with lithium-ion batteries. They were very happy. They weighed half as much, took up half the space, and were going to last twice as long. And these are basically on the outside of the space station storing the solar energy. So let's get back to climate change. You all know, as I say, the sun shines when it wants to, so we have to store it. There are a number of ways of storing this energy, and it depends really on the season of the year. So by far the lowest cost today is pumped hydro, and I show you a facility in New York State. Maybe Michigan's a bit too flat for this, I don't know. But the real issue, pumped hydro you use for seasonal storage. So you use much more power in the middle of the winter, in the middle of the summer than you do in the spring and the fall. So you fill up the reservoir by pumping water up in the spring and fall and then take it out in the winter and summer. You can also use it on a daily basis. But this is a typical facility. This is halfway between my campus and the state capitol. It can generate a gigawatt of power until it empties the reservoir. A slight challenge, it takes about 2 minutes to start up. So this is by far the largest means of storing energy, both in the US and throughout the world. It's not clear there's going to be any more of these built because of environmental and other reasons. But what they are doing is upgrading all the turbines in them. Right now, the turbines are, I think, 71% efficient. So you get 71% of the energy out that you put in by pumping the water up there. And people are looking at, can they enhance the size a little bit of the present ones. I already discussed really the batteries, where we're going to store the energy as chemical energy. This is by far the most flexible. And then the third area is flywheels. There are a couple of these in the world. They're high cost initially, so it's not clear anybody can make any money. The one in Albany, New York, went bankrupt. Another company took it over because they didn't have to pay for it. They're now making money very well. These are used more for what we call frequency control, not for long-term storage. And the real issue here is they're like a huge hand grenade, so they're kept in concrete bunkers. So again, you can't use these in vehicles or trains or buses or anything like that. So let's get back to storage on the grid. I show you a facility here. This is the largest in the world. This is 1.2 gigawatt hours. This is just south of San Francisco. They've already got permission to increase this to 5 to 6 gigawatt hours. And this is not enough to store the solar energy excess they're having now in California. So many people have put solar on their roofs. They're actually having to just waste it in the middle of the day. So California right now on a sunny day is 100% renewable in the middle of the day. So that's this one. Over here I show you, and this is maybe 10 years old now. This is a wind farm in West Virginia. If you actually measure energy coming from the wind, it's going up and down second by second. So you have to have some means of smoothing it, and they use batteries. These batteries can also shift the load by about 6 hours. So they're becoming fairly common. And in fact, in Binghamton, they're now in the planning stage to put a 400 megawatt hour storage facility just north of a shopping mall. So the vendors can make money as of today. And it's lower cost now to put wind storage in place than to put coal power plants in. So I think coal power plants in most parts of this country are finished. You're not going to see any more installations. So let me get to the batteries now. I expect everyone in this audience has a lithium-ion battery on their person. Several of you probably have 2 or 3. But you don't have lithium batteries. You have lithium-ion batteries. So in the lithium-ion battery, there should be no lithium metal at all. This is what happens if you have lithium metal. When you recharge them, you get these dendrites formed. These dendrites will short between this electrode and the other electrode, and this is the result. They catch fire. And this was some solid-state batteries built by Avastor in Canada and used by AT&T in housing developments in the South. So essentially lithium batteries themselves ceased being sold in the US by about the mid-80s, early 90s. So everything now is a lithium-ion battery. So what is a lithium-ion battery? This is a very simple schematic. They're all based on what we call intercalation chemistry. All of you know what February 29th is. It's intercalated that day into the leap year, to put the 29th day in. If you look in an old dictionary, that's the definition you will get of intercalation. If you go on Google now, it will give the chemical definition, which is exactly the same thing. You're going to intercalate a species into a host lattice. If you take it back out, you won't be able to tell the difference. So this is the technology used in lithium-ion batteries. And this is why you can recharge them so many times, because the lithium ions do not change the structure. So if you, for example, X-ray either one of these electrodes, they'll look exactly the same before and after you've used the battery. So for those of you not familiar with batteries, we have two electrodes, the anode. This is where the lithium will be stored, where it's fully charged. On this side is the cathode, and this is where the lithium ions will migrate to through the electrolyte here. As we discharge it, the electrons go through your external circuit. So in principle, very simple, but in practice, very complicated, because these materials are not stable in contact with each other. So you have to make films on each one of these surfaces. You have to use an electrolyte here that's not water like in your lead acid. So this is today an organic. So we have to make sure all those work together. And for our efforts, the three of us did different parts of this. So this is Akira Yoshino from industry in Japan, and John Goodenough and myself, just after we gave our lectures in Sweden. So for those of you who aren't aware, you get awarded a Nobel Prize, but you don't actually get it until you've given your lecture. That's the only thing you have to do. You don't have to show up to the ceremony or anything else, but you have to give that lecture. And a few of the literature folks, I think, balked at doing that until they realized they weren't going to get the money. So this is the various steps in the lithium-ion battery. So it started really in 1972, and I should say, when I joined the company, it was Esso. It went to Exxon now, it's ExxonMobil. And we had the idea of using lithium. We switched very quickly to lithium aluminum to stop those dendrites forming. Akira Yoshino in Japan worked on carbon materials. That's the layered materials I showed you, and that made it stable. The issue here, this takes up half the volume of the cell. So if you can take that carbon out, your iPhone would last twice as long. So our goal today is take it back out, and this is what we're working on today. On the cathode side, I worked on those single crystals I show you, titanium disulfide. John Goodenough was at Oxford at the time, and he was working on lithium cobalt oxide and its magnetic behavior. As I said, I was working on superconductors. He's working on magnetic behavior. He said, oh, my structure's the same as Stan's. I'm going to try it in the battery. No chemist would try this material like this, because we've been taught cobalt-4 doesn't exist. Therefore, you can't take lithium out of this and make cobalt-4. John was a physicist. He didn't know better. And he'll agree with me. But the strange thing, he was also the professor of the inorganic chemistry department at Oxford at the time. But he showed it did work. And this is the material still used in your phones today, because it has the highest energy per unit volume. Okay. As we all know, cobalt has many issues, including child labor. It's expensive. So most of the batteries nowadays use a mixture of nickel, manganese, and cobalt, or in the case of Tesla, nickel, aluminum, and some cobalt. So the goal of the field is to get the cobalt out of the batteries. John also came up with these, what we call LFPs. These are lithium iron phosphates, naturally occurring minerals. These also work very well, but their energy is only half of these. So for a lot of applications, it's not realistic or economic. So what we've been working on is The phosphates are nice and stable, they're safe. Can we stuff 2 lithium ions in there and get the energy density up? So we've been working on these vanadium compounds. Don't worry about all the numbers on here. It doesn't matter. The only thing that matters, look at the numbers in here, this red egg-shaped box. This percentage here is the percentage you get in a commercial battery relative to the theoretical energy density you should get. So you can see the worst case is 11%, the best is 25%, and this is on a volumetric basis. On the weight basis, it's the same thing. So there's a huge opportunity still of at least doubling those numbers, and I'm part of what's called a Battery 500 consortium, and the goal is to get this up to 500, this up to 50%. So there's a lot of opportunity for more research, but we've got to take some of that carbon out. We've got to make all the materials work better to do that. And I gave you a few examples of what we might do here. So there's a lot of opportunity for chemists, material scientists, and physicists to come up with new materials, and for the engineers to design the batteries so they take up less, well, the active materials take up more space, and the stuff you don't really need take up less space. But that's what we're trying to do today. And we're doing that within the Battery 500 consortium. So what we're doing there is looking at this NMC, nickel, manganese, and cobalt, and trying to determine what is the best amount of each one of these elements. And I'll show you first, this is the structure of the material. This nickel, manganese, cobalt, here's the lithium ion. All you're doing is moving these in and out continuously. And you see here, this is the amount of nickel, and as you put more nickel in, the energy density goes up, so you store more energy. But what happens is, this is the temperature at which these materials let oxygen out. Oxygen leads to fires. So the more nickel you put in, the lower the temperature. So this releases oxygen at 200 degrees. If you've only got a third of a nickel in there, it's over 300 degrees. So there's a huge dependence on the nickel content. So our goal is to increase the nickel content as much as we can, but also stabilize it against loss of lithium. So for the materials folks in the audience, a lithium-ion battery is a metastable situation. Every component will react with the other if we don't have protective films. And these layered oxides, if you take the lithium out, if you've got a catalyst in there, these will give off oxygen at room temperature. But it's a slow kinetic process. So what we've been doing in Battery 500 is trying to improve the energy density. Again, for the non-chemists here, don't worry about the figures here, just look at the trends. So we're trying to make longer lifetime, that means more charges and discharges, increase the energy density. And we started this project in 2016. So you can see we've gone from 50 cycles, a year later up to 250. We achieved the same amount in 2019, but now we'd pushed the energy density from 300 to 350. We're up to here in 2020, and right now in 2022, this is about up to close to 1,000 charges and discharges. We have got higher energy densities, but I'm not allowed to talk about that until we publish it. But this work is led by Jay Xiao, an ex-PhD student of mine. She's at Pacific Northwest National Lab. We make the materials. She makes these batteries, these what we call pouch cells. Then she sends these pouch cells to Idaho National Lab to be tested. So each bit of this is done in a different place. So the numbers are true and real, and no one's, can we say, cooking the books to make things look better. So if you read press releases on great new batteries, don't believe them unless a third party has done independent testing of them. Okay. So just to mention, these are what the materials look like in the batteries. We call these meatballs. So they pack together well, and the commercial supply will have different sizes of these, so they pack even tighter. But this does give some problems, which I won't go into today. But these are the materials we're looking at. We're trying to push all the limits. And for those of you in the battery area, I should say from early days here, we have changed both from carbon anode to a pure lithium metal anode, and we've changed the electrolytes from carbonates to ethers. So we've had to make all these changes to make these accomplishments. So as I said, now we're interested really to move off oxides, which we think are unstable. We want to move off cobalt, and we want to move off nickel. So we really want to work, if we can, on iron-based materials. If iron-based works well, as we showed it did with lithium iron phosphate, it's too low in energy density, so can we now increase it? So we've been working on this material, and I should say, for those of you who are familiar with the field, we worked in TiS2. The folks up in Canada worked on MOS2. This is molybdenite, a naturally occurring mineral they can dig out of the ground in British Columbia. So these batteries were sold for manufactured by many years by eMoly using natural molybdenum disulfide. So our goal was to test this. Clearly, I wouldn't be talking about it unless we had done it. So these are two of our students who got the prize from the Department of Energy for having made this accomplishment. And this was the only battery accomplishments in this 2018 report that came out in 2019. But all these major changes really take a whole group to do it. Not individual research groups can do this. So you need the best research scientists in the world who are experts in making things, doing the theory, and Katsura Thornton was part of our EFRC doing this. And then you need the scientists at the beam lines who can really make the in situ measurements to see what is happening on these. And these were some, of our collaborators here. So this was the description of it. So we made these materials. It's easy for me to talk about it because I don't spend years trying to make them. But we had students, PhD students, who made this material, and these are little cuboids. They're about 100 nanometers in size. And it took them about 3 to 4 years before we could make materials that really worked well in batteries. Because those of you who are electrical folks will know phosphates are outstanding electronic insulators. So remember, in the battery, we're moving lithium ions in and out. You want the electrons to do the work. They have to move in and out as well. So to make this work, we in fact coated these materials with graphene, very thin film of graphene. This made them sufficiently conductive. And then this is the data we got out. Again, don't worry about the details. The only thing to think about is the black line here is the first charge, discharge and charge. The purple line is the 50th, and the purple lines in the middle here are closer together than the first one, which means it's better on the 50th cycle than it is on the first one. So we had proof of principle. We can, in fact, put two lithium ions into a structure without damaging that structure in any way. It doesn't mean this is commercially viable yet. Those of you who are in catalysis will know these vanadilyl phosphates are commercial oxidation catalysts. So a challenge we have is that they'll always get, when we charge it, we get more capacity apparently than we discharge it, but on discharging we get the theoretical amount out. So what is happening on charge is reacting with the solvent. So we're trying to solve that right now. But this just shows you one example. There's plenty of opportunities for people to come up with totally new cathodes, and what we need are very stable cathodes that are not going to evolve oxygen and that cannot support fires. So let me explain really one of the challenges. We've got climate change. We'd like to put batteries in there for energy storage, but we can't do it in this country. So right now, a lot of ideas in academia, startup companies, industries. Two of us in New York State, RIT and at university, we can make small cells. Now we have dry rooms and basically pilot production lines, but we can't make many of them. And New York Best, which is a battery consortium that can then test these cells in Rochester. But if a company comes in and says, we want 1,000 cells to prototype, to let our customers test, What they have to do, they have to send them to Asia, mostly South Korea or China. The Chinese then build them, they build the cells, then they get shipped back to the US for our electronics, for the grid, the military, and for these vehicles I've shown you before. So everything goes through parts of Asia right now, and you're hearing about gigafactories being built in the United States. Those, for the most part, are being built by Asian companies. So they may be made in America, but they're not made by Americans, and that's one of the things we're trying to change. So we have this big conundrum at the moment. So the real issue is, if you like, is the global supply chain is not working. You all learned that when COVID came. Now, where did you get your masks from, if you could get them? It turned out most of the American suppliers were in fact manufacturing them in China. That has all changed now. So we found out, now that doesn't happen. It wasn't the Chinese being nasty. They needed them for their own people. We see it now in the semiconductors. There's not enough for the cars, so Detroit has slowed down. And if you want to get an EV out of Detroit, I think there's a 15-month waiting period right now, because they can't get enough semiconductors and enough batteries. So what we have to change is remove the global supply chain, put in what we call regional supply chains, and we're having a lot of discussion with the federal government. Stop talking about United States. Talk initially about North America, and then in the end, all of America. Because in North America, there's lots of nickel, there's lots of carbon, just a few miles north of here, over in Canada. So we have to work with our Canadian colleagues. It turns out there's a lot of clean hydropower in Canada as well to process these materials. So we think we should work with Canadians first, and as we progress, then we need to bring in the South Americans with their lithium, and then other, can we see, friendlier nations like Australia can also make a lot of lithium. So we have to build up regional supply chains. Europe is doing that. They've got a national program in Europe where the materials are coming from Scandinavia. They're getting initial processing using clean hydropower in Scandinavia. Then the materials come down to Central Europe to be turned into batteries. One of the issues is, if you look at some of the materials, people have calculated, say, nickel or some of the graphite travels about 50,000 miles from the mine to when it's actually in the commercial battery in the car. And this is not sustainable. It takes up too much energy. What we as scientists have to do, we have to look at what's in our batteries, what's in our electric motors, and research out all the critical materials. Whether it's rare earths in the motors, find the substitute. In the batteries, find the substitute for cobalt. No, I'm sure we can do that. We've gone from commercially from 1/3 cobalt. It's now down to about 10 or 15% cobalt. And we can go the rest of the way. Things like graphite, we should be able to make in this country. A lot of the graphite is artificial. It's made by chemical plants or refineries, mostly in Japan and China. We could, I think, easily do it in this country with a bit of an incentive. And if you look at this state, you are the epicenter of the internal combustion engine. Can you make that transfer to an electrified economy? Clearly, no. Can be done. I visited VW's facility in Germany just before COVID came, and their major manufacturing plant there, that's split off half of it, and they're training all the present employees to make electric motors and the parts for electric vehicles. They also had a test bed there for testing out their own batteries. So the Germans are serious. Maybe they feel more threatened than we do. I think more than 10% of their population is employed in the auto industry, and they can't afford to have that to go offshore. So there are many challenges in this area. One I haven't really talked about is the amount of energy it takes. If If you want a 1 kilowatt hour battery, it will take between 60 and 80 kilowatt hours to make it if you start from the mine and go all the way to the finished product. So we need to look at cleaner, less energetic ways of making those materials. And clearly one way is to go away from carbothermal. That means stop using coal and cokes to reduce, for example, the metal oxides to the metals. Find new electrochemical means of doing that, where we can use clean energy to do it and make no CO2 at all. So there are plenty of opportunities for researchers, chemists, material scientists, and I would say the geology mining folks to actually develop totally new manufacturing techniques at the mine. And we're encouraging places like Chile to do the upgrading of the lithium right at the source. This will mean they'll make more profit, and we won't have to ship as much material to the rest of the world to actually make the batteries. We'll be able to make the lithium carbonate and lithium hydroxide right at the mine. So this is what we're proposing. I showed you that big gap a minute ago. This big gap, Asia in the middle, what we're proposing is to change that and put New York in the middle. And I think there's a similar effort in Michigan to do the same thing, to put Michigan in the middle. And what we're proposing there is to build a facility, and we're going to use some old IBM manufacturing plants. IBM started out in the Binghamton area. They left about 10, 15 years ago when they got out of manufacturing. They don't make anything anymore. They just sell knowledge and sell storage and so on. Okay. So our goal was to build a facility so we could actually get totally new manufacturing approaches, get rid of the stuff that's now 30 years old, leapfrog the Asians, come up with new intellectual property, but at the same time, build in what we call full-size cell lines so companies can make, say, 1,000 batteries so they can really do full prototype testing, which they can't do in this country at the moment. So we have a proposal into the economic development folks in Washington to do this. To do this takes about $100 million. This is why individual battery companies cannot do it themselves. So what we're hoping to do is build such a facility so a company can come in, use it, say, for a week or two or a month, test out their systems, and if it works well, then sell their ideas to a large company and start building a gigafactory. So we're going to be working through industry. This is our New York Battery Consortium, which is an industrial consortium. We can do cell testing up in Rochester, and the largest also recycling facility in the United States is now Lithium Cycle, which is in the old Kodak Park in Rochester. And we can do advanced characterization. For all new battery materials and the batteries themselves, you've got to look at them whilst they're working. So you need a national lab with their synchrotron facilities. So what we hope to do is have commercial manufacturing in North America and eventually by US companies. And New York State, similar to California, has, some would say, extreme green goals. I said New York doesn't generate any electricity from coal today. They have, I think, 6 gigawatts of storage to be on the grid in the next 5 years. If it's 4 hours, that means 24 gigawatt hours on there. Electricity grid will be 70 or 80% green in the next 7 or 8 years. And at the same time, they're closing down 1 or 2 of the nuclear power plants, which is making it more difficult. But they're putting offshore wind in, so New York State is going green as fast as they can. And the big issue every state in this country has is there's not a federal energy policy. You know, Europe has one, everyone in Europe got together. Here our federal government policy changes at least every 4 years and maybe every 2 years as the government changes, and you can't run an operation that way. So what's the future for us? I think I define it fairly clearly here. the batteries we have today, they're going to control for the next 5 or 10 years. They're going to get better, but it's not going to be a replacement. Partly because we made the invention in '72. It took to '91 to make an economically viable battery system, 20 years. Any new system coming out today will be faster. It's going to still take 5 to 10 years. So you're not going to see solid-state cells, sodium cells, or redox flow batteries within 5 or 10 years, just because of the time it takes to ramp up, and because lithium-ion batteries are so low cost now. Those new systems had to find a high-price market to break into the market until they can ramp up production. So what we hope to do is leapfrog the Asians. We need a good supply chain, and a lot of people I've talked to here already realize the US is putting a few $1 billion into this. A lot of the calls for proposals are out there now. If they're not out there now, they're going to be out there in the next month or two. So it's a huge effort here. Just like in the old Sputnik era, we wait, and then say, whoops, now we've got to catch up. And so this is what the country is trying to do. We've got to come up with clean mining, not the old ways, with clean energy. We've got to do much more on the recycling if we're going to make these things sustainable. There's probably in some places around this country more cobalt in the dumps than there is cobalt in the mines in the Congo. And though it's valuable, it has to be recycled back into the system. So I said we hope to build a capability in Endicott, which is where IBM was. As we had Senator Schumer visit us 2 weeks ago, our goal is to bet on every battery that goes in an electric vehicle in Detroit or anywhere else, that will have a stamp on it, made in America. So we stop importing all this stuff. And we hope to build a better ecosystem for clean energy so we can get all the bits and pieces together. If you look at what a battery contains, it's got lots of little pieces, straps, cases. There's nobody making those, but we're looking at industries that do that for other purposes and slowly retraining them to get into the battery area. So just a message for the younger folks here. At the Nobel ceremony, each group of winners has to give a 3-minute speech at the banquet. There's about 1,000 people at the banquet, plus the king, queen, and the princesses, and so on. And we have to explain, what's important about what we're doing. But what we wanted to mention really was you cannot do research alone these days. So you need interdisciplinary, and I've talked to folks today. If you get a chemistry PhD, you're not going to make a career in chemistry. You're going to make a career at the boundaries of chemistry and something else, whether it's materials or whether it's the medical industry. Similarly, you just look around you. How many people here were born in the US? Probably less than half of you. And in the battery area where we've done this research, we work around the globe because different people have different skills. So to go into the detail here, I'm a chemist. John Goodenough was a physicist, and Akira Yoshino was an engineer. I came from the UK, but made my inventions in the US. John Goodenough was born in Germany of US parents. Is an American, but he made his inventions at Oxford in England, the critical ones. So now we kind of stirred the pot a bit, and Akira Yoshino was in industry in Japan and made his inventions there. I've already talked about the global warming, which I call global messing up. But 2 points we always want to mention. Because we're an international community, it's essential that researchers understand culture. Asians don't think the same way as Americans, and even Europeans don't think quite the same way. So we have to understand how they work together. And I spent 2.5 months, 20 years ago in Japan on the GISPS scholarship. And my host and I had to get together to work on the students because they didn't dare ask questions. No, you never question your professor in Japan. So we had to set it up so I would question him, then he would question me, and then we'd point to a student in the audience, now it's your turn to ask a question. And in the end, we got a lot of them asking questions, and this is important. And when I was journal editor at the same time, Americans interpret the data and say what it means. At that time, the Asians did not. They said, let the data speak for itself. So, Americans reading the journals say, well, you only did half the work. So I think we had to change that culture as well. The other thing all scientists and engineers have to do is convince their neighbors, their politicians, that facts do matter. And even though we know we shouldn't tell them what to do, we should say at least listen to us. Global warming, climate change is clearly happening despite what people want. And if ex-president looked out of his house in Florida, he would see the waters come up a foot or two in the last 10 years. And in the next 10 years, his house is going to be underwater. I just want to finish by showing that the Nobel ceremony, which lasts about 10 days, is not a one-day event, is a family event. Everybody gets involved, and the men are much luckier than the women. There are tailors there, and you go to them, and they fit you up in all your outfits. The women have to get a different outfit and bring it with them. And there's about at least 3 occasions, so women don't wear the same outfit on 3 different nights. The men clearly do. So this is one of the first few times when my wife and I had to actually check our bags when we went there, because things wouldn't fit on. But there are red carpets, and there are paparazzi trying to take pictures. And at Binghamton, my president said, we've put your name on the lab. So I teased him, you mean I've got so old I can't find it? You need to put my name there. So I will stop there and try to answer any questions you might have. Thank you very much.
Thank you, Professor Whittingham, for that presentation. So we have time for questions, and the way it will work is we have 2 volunteers. Both of them are PhDs. These are microphone runners. And what they have in their hand is called Catch Me, or Catch Box or something. So Tim, can you do a demonstration?
This is a microphone. This is how you talk into a microphone. This is not how you talk into a... This is how you talk into a microphone. Also, raise your hand. You're not a T-Rex. This is not how you raise your hand. This is how you say you have a question, and we will come find you.
Okay, questions. If you just raise your hand, they will bring the microphone to you.
Hello, thank you so much for the lovely talk. It was really, really interesting to learn how lithium-ion batteries will play into renewable energy. I actually was curious if you had any insight on how the form of the electrolyte will kind of like play into that, like whether it'll be a liquid electrolyte or a solid state electrolyte or a gel electrolyte even. Thank you.
So today, all the batteries are liquid electrolytes, or we can call them liquid gel, but they're liquid-like. That gives some issues on safety because they're organics, they can catch fire. So the goal is to go to all solid-state systems. So we'll have a solid electrolyte, and then we'll use lithium metal, which will increase the energy density. But you saw on that fire I showed you from the AT&T cells, solid electrolyte is not necessarily safer. And there's been a number of fires with the solid electrolytes built by the French company in their own buses and Mercedes buses. So we still have to worry about any organic type system. So if it's a solid polymer, there's still an issue that it might catch fire. And there's a lot of talk that inorganic solids as the electrolyte are the way to go. But dendrites like growing down grain boundaries extremely fast, so we have to solve the problem there. We may be able to cut them off better than in the polymer ones. But the goal is to go to all solid state. Today, everything essentially is a liquid or a gel-like liquid. If you open up a lithium-ion cell, nothing will drip out, especially a dry cell. But there's enough there to get the fire going.
Thank you. Great lecture. I just had a question. In the cases like for the grid, where bulk is not an issue, are there alternative solutions, maybe more old-fashioned, like salt water, lead acid, that kind of thing?
You say bulk is not an issue, but in most cases, bulk is an issue. So in this California system, it's all lithium-ion. They put lithium-ion because right now it's lowest cost per kilowatt hour. Or what the grid will look at is lifetime cost. Lithium-ion batteries, you don't really have to look after. So there's a system near Saratoga Springs we visited just before COVID. And we asked them, what's the maintenance? Well, they say, we watch these from our home office on the computer. We don't have to do anything except order the folks who mow the lawn around them to keep it clean. So lithium-ion battery is good. Lead acid, remember you've got water in there, you have to top up the water, and there's maintenance issues. They tried those out in buses and they were dismal maintenance failure. Lead acid was tried out, I think, in Puerto Rico many years ago, and serious corrosion problems from the salt air. So people don't think that in the end, a long-lived lead acid battery is probably more expensive than a lithium-ion battery. And new systems, they will come on board, but they've got to get the price down so they're competitive with lithium-ion. And I think the difference you're going to see in the grid, eventually they'll use lower cost materials for the grid storage than they do for electric vehicles. Right now they're using essentially the same source of batteries.
Hello. Thank you for the talk. I was curious particularly about EV applications where electric vehicles are noted to be a lot heavier than a lot of the internal combustion engines, and that has taking a toll on our infrastructure systems. And I study microplastics, and the heavier the vehicle, the more microplastics that a vehicle emits. I was curious if these new batteries aiming towards lighter would actually help to reduce the weight of these vehicles, or how that interacts into that system as well.
It all depends on the customer. You can make the vehicle lighter by putting less battery in there. So you can, no. So, and I'm serious, no, if you want to get a high-end Tesla, go 400 miles, it's going to weigh a lot more than a Tesla 3 or one of the GM cars that may only go 200 miles. So there's very much a trade-off in there, and clearly on a smaller car, you can't fit so many batteries in it. My understanding is the Hummer SUV, the EV version, is going to weigh about, is it 7 or 8 tons? Because they're putting so many batteries in it. But remember that your own cars don't really damage the road that much. It's the big 16-wheelers that do most of the damage to the road. But you have to worry about that. But no, it's in the end, it's what does the customer want, and is the customer willing to pay for it?
Thank you for the excellent talk, Professor. I was really here.
Oh.
Yeah, I was really interested in the sustainable ecosystem of the lithium infrastructure you were talking about. What role would the recycling of batteries play in grid storage, and what do you think about the current status, and where do you want it to go?
So recycling is absolutely critical for sustainability, and the perception is that in about 10 years' time, most of the lithium for new batteries and the nickel will come from recycled batteries. It is commercially viable today. As I said, Lithium Cycle, which is a Toronto-based company, has a major recycling facility in Rochester, New York. That's what they call their hub. Then they have spokes in Arizona and in Texas. So they're recycling as much as they can of the battery. And they're making money doing it today. There are other smaller companies, one by one of my ex-students in Blacksburg, Virginia. What they're hoping to do is actually take the material off the electrodes of the present batteries and upgrade it so it can be used again without turning it into basically what we call a mineral ore, which is a lot of what the companies are doing. And it's important to realize in a battery plant today, there's about 10 to 20% wastage in the manufacturing process. And that's the easiest material to recycle because it hasn't been damaged, it hasn't been changed. So you just have to get it off the electrodes and then put it back into the supply chain. And I should say the copper electrodes, I'm told they're worth a lot of money. So they want to recycle that copper. At the same time, they'll recycle all the lithium too. So the goal is to make it more sustainable. In about 10 or so years, you're going to see a lot of today's Teslas and others, the batteries being recycled, and those have a lot of cobalt in them.
Hi, so here. First of all, thank you so much, sir, for the lovely lecture. And I have a rather general question. So I think you mentioned in your slides about the industry trying to get rid of like the Asian production, especially since during pandemic, the transportation is being low efficiency. And however, I think like the pandemic will not last forever. So do you think there is possibility that instead of getting more localized, we can actually enhance this kind of cooperation internationally? Thank you.
I think over the last month, we've learned that that's not possible. Now, we've seen what the Germans are going through with Russia. So if there's any disruption anywhere that can disrupt, they can't get the oil, they can't get the gas. You're all seeing that Russia's stopping all the wheat and corn in Ukraine from being exported, so all the food prices are going up. It's okay to have a certain percentage coming from any one country. You can't afford to have 90+% coming from any one region or any one country. It's just not secure either politically or economically.
Okay, so I have a question down here. Yeah, thank you again for the talk, Professor. Hopefully 2 quick questions. One, if you had to start over as a PhD student, what advice would you give to yourself? And also, what drives you to do research?
So as a PhD student, I tell every one of them, do something that excites you. Don't do it for the money, and don't do it necessarily totally because your boss said this is what you do, A, B, C, D. You got to do something that excites you, and you have to take risks. You're not going to make breakthroughs unless you take risks, so don't be too conservative. And remember what Einstein said. Imagination is more important than knowledge. You can look, particularly these days, you can look up knowledge on Google, but you need to dream of what you want to do. And dream something you want to do, okay? And then work out with your faculty and the sponsors how you do it. But this field has huge opportunities everywhere.
Thank you very much for the great lecture, Professor. I would like to ask your opinion or insight on alternative chemistries like silicon or sulfur-based batteries.
So although lithium-ion dominates today, we have to look at alternatives. As I said, half the volume of the lithium-ion battery is taken up by the graphite anode. If we can make silicon work or make some other material work, ultimately we'd like to go to lithium metal. It's not clear how easy that's going to be, but we have to make these other anodes work. We've got to do research on them. We've got to do research on alternatives like sodium ion, but we have to be very careful there. Sodium ion has low energy density, so don't use the same cathodes as you use on lithium, because the savings you're going to have on the sodium will be more than taken up by the extra nickel and so on you're using. I think we've already discussed long-term, the ideal solution would be a lithium-sulfur or a sodium-sulfur battery. The sulfur is essentially free. If you go to any refinery, they'll probably pay you to take it away. So no, but the technical challenges are horrendous. No, sulfur doesn't like conducting lithium ions. It doesn't like conducting electrons. So you've got to find a way of making it more conductive. You've also got to find a way so it doesn't get across to the anode and basically leak the energy out that way. But battery 500, half its efforts on lithium sulfur, half's on the layered oxides. I know there's a number of programs here and elsewhere on lithium sulfur. You have to be very careful not to overhype. The group in Tucson has stopped working on lithium sulfur. The British company who was marketing lithium sulfur very actively went bankrupt. So never promise to a customer more than you can actually deliver, because in the end it will catch up with you. But lithium sulfur is the goal, and we should be doing more fundamental research on it.
Hi, Dr. Whittingham. Thanks for your today's fantastic lecture here at University of Michigan. I'm wondering, what do you think about information technology and computing will affect and helping the trends for development for new lithium-ion batteries or batteries in general?
So if you're talking about the role of theory, machine learning, and all those things,
yeah,
they all play a role. And as I showed in one of these slides, on our EFRC, Nexi, we had as many, I think, theorists and modelers on that program as we did experimentalists. So all that activity is critically important. We have to be careful we don't overdo it, because the challenge we found is theory can give you some numbers, but it can't necessarily predict everything. But what we hope that theory and machine learning will do, if I as an experimentalist have 6 options, tell me, you theorists, machine learners, which is the best option for me to put my students on. But we still have to do, I think, the experimental work.
This is more about the research and development. But for example, in today's electric vehicles industries, like Tesla or GM, they have the BMS for they utilize such a information-based method for improving the efficiency, energy efficiency.
Right.
So how does that compare to the chemical or chemistry-based methods?
Basically, in all these systems, now whether it's my iPhone or the electric vehicle, you've got a trade-off between all the electronics, the BMS, and the battery. Which one can you improve the most? And if you talk to Apple, I suspect you'll find out, if they will tell you, which they won't, that it's really improvement in the electronics, the chips, that are giving you the longer life of the cell phones. So it's critical in the battery. The same, the electric motors have to be more efficient, and Tesla has a big advantage right now. They're using silicon carbide components, which gives them more efficient motor systems. You have to have more efficient BMS. And I would say more than half of the battery issues we've had are related to the electronic controls or shorting in some of those. So both the electronics and the battery itself, they're equally important, and one can't go ahead without the other.
Okay. Thank you so much.
Hello, and thank you for the lecture, very interesting. My question is about one slide that you had about renewable storage. Because the renewable form of energy can't handle intermittency very well, and especially if there is a high power release of energy that we need. Do you think that battery would keep up with this demand in the future, or does it need a revolutionary discovery in that field?
I think we have to look at all different forms of energy storage. People have looked at flywheels extensively. They've looked at compressed air. Compressed air doesn't really work well. It's only used in combination with a gas-fired power plant. They looked at gravity systems, and those again need lots of space. So we have to look at all the different opportunities, and we have maybe do a little dreaming like the British at one point. They didn't want ugly-looking pumped hydro. So they have a pumped hydro system within Mount Snowdonia. It's all inside the mountain. So from the outside, you don't see it. But anything creative to do energy storage, I think, is critical. Don't say batteries are the only way to go.
I know this isn't a very fancy question, but I was wondering what kind of mindset you take when your research doesn't feel like it's going to go anywhere, or it feels like it's taking too long, or it isn't really working out.
That's not a question I can easily answer, because I have a group of graduate students, and hopefully at least one of them has good research going on. But what I tell my graduate students, you have your major project, have a side project, a smaller one. So if you get stuck on your major one, spend some time on the other one. And then you may find a solution to the major one. But don't put all your eggs in one basket, because you can get stuck, and you can get stuck for months on because something won't work out. But dream about what you want to do and have a number of opportunities all going at the same time. But put your main emphasis on one thing, but don't cut out everything else.
So you talked about the million-mile battery. Do you think that batteries will actually need to be that far in the future, or do you think we could get away with even just half that or a quarter of that?
You'll have to talk to the utilities on that, because when we talk about a million-mile battery, we're talking about a battery that will last 15 to 20 years, being charged and discharged essentially every day if the utility wants to do it. So it just means a very long-lived battery. And I think Jeff Don, who probably started that terminology, got a battery and cycled it enough times that it would have actually driven a car that far. But that's just a convenient thing, term to use to sell it to Congress and the politicians. It's the same reason why battery 500 is called the battery 500. It's 500 watt-hours per kilogram. In the car, you don't care so much about the weight as the volume. But we're told they had to sell it that way because all the politicians know about the Indianapolis 500 car race. So no, 500 is a term they understand.
I was just wondering, do you see a future, or do you see the benefits of batteries with like aqueous systems, or systems that are using less harmful solvents like NMP?
Yeah. So one of the goals of our major project, and I think Europeans are already doing this, is to get NMP totally out of the manufacturing process. So remember, there's no NMP in your batteries. It's used to coat the electrodes, and then you evaporate it out, and then you have to recover it because it's toxic. So in our planned facility up in our county, the NMP recovery equipment is well over $1 million. So there's the economic incentives as well as health incentives to get the NMP out. Can we find another solvent that'll work just as well? And today, the graphitic anodes are all used an aqueous-based solvent. So I think eventually we'll find something. If we can do it without using any solvents, all the better we'll save energy on evaporating it out afterwards. So we have to get that out. The other part of your question was?
Sorry, that took the cube away from me. Do you see like that the environmental benefits of using an aqueous system is going to outweigh the maybe downfalls that we might see with aqueous systems?
So on the aqueous, the negative aqueous systems, they are much lower energy density. So people will say they're lower cost, but it's the same issue with sodium. Actual battery itself may be lower cost, but you've still got all the surrounding infrastructure. So if you have an aqueous system with half the energy density, your surrounding infrastructure will be twice as big. So that'll cost you more money. So it depends whether you've got cheap land, cheap steel to build a system with. So it's very much a trade-off. And an aqueous system, I think it has to be totally self-contained, so you don't have to keep topping it up as the water evaporates. But we have to look at everything, and aqueous is clearly one way to go.
Thank you again for coming and speaking today. I'm curious to hear what you think, how far away we are from the limits of lithium-ion battery technology, and if there are segments or industries that are not best solved through battery technology and other sustainable solutions.
So we're nowhere near the limits, so we can at least double it, and if we go to lithium sulfur, maybe we can triple it. Batteries are not viable for, can we say, long or medium distance air travel. You'll be carrying more batteries than you'll be carrying cargo. For short hops, 100, 200 miles, they're viable, particularly if you don't have to have a pilot. So there are planes starting to test fly now, which are 9-passenger planes up in Washington State. And they're thinking of taking these from, say, the mainland to islands offshore. And in particularly, rescue squads are looking for electric vehicles where they can take medical supplies and, if necessary, a medic up into the mountains to help somebody. So there are specialized applications there. Your big 16-wheeler trucks, again, they're not viable batteries. You'd be carrying more batteries. So the thinking there is you would have maybe a hydrogen fuel cell connected to a battery. So remember, a fuel cell cannot work effectively because it can't give acceleration. A fuel cell operates best at constant output. It can't do regenerative braking. So the thing is, you'd have a fuel cell and the battery pack with it, and you'd use those for the large trucks, and you'd refuel the hydrogen in them from hydrogen generated by clean energy at, say, the rest stops on the interstate highways. But there are some applications where batteries, no, just won't work. And I think it's the same thing we're talking large ocean liners.
Hello, here. Thanks a lot for the nice talk. I have a question for fast charging technology. So right now, the cell phone vendors are advocating the benefits for fast charging, like you can charge to 90% in 1 hour. But they usually results in some results from the large charging current density, which can damage the electrode material. So do you have any ideas on how to break this trade-off on fast charging? Thank you.
Yeah. Everything you have in the battery or any device, you've got trade-offs. Do you want fast charging? Do you want longer life? Do you want higher energy density? So in my mind, no. My little watch here, I can charge essentially in less than 1 hour. I think if your iPhone, you can charge it in less than an hour to 80% of the capacity. But if you actually look at what Apple and Samsung are doing, they have software in there which moderates the charging rate so it extends the lifetime of the battery. So if you fast charge a lot, you will damage the battery for sure. So everything is a trade-off. You can't have high power, high energy, fast charging all at the same time. You've got to have one or the other. So there's a lot of interest in single crystal materials. These will give extremely long lifetime, but because the surface area is less, they won't be so good for fast charging. And remember, your gas station operators, service station, whatever they're going to be called in the future, don't want you to do fast charging. They want you to go in there, plug your car in, go to the restroom, go and buy a sandwich or two, and buy a few other things inside that. So that's where they make their money. So not everybody is on the same side. And if you really want fast charging in the car, just get a piece of paper out and your pen. If you're going to charge, say, a 100 kilowatt hour battery in 10 minutes, work out what voltage you need and what current you need, and therefore what size cable you need to connect to your car to do it. It's not readily viable, even though people are talking about it for a large vehicle.
Let's take one last question.
Right. What is the, thank you, Professor. What is the primary mode by which you are trying to improve lithium-ion batteries? Like, what is the main roadblock that you're trying to overcome?
It's reactivity between the different components. So we're mostly working on the high nickel materials. They react with the electrolyte solvents, so we're trying to come up with new protective coatings. Now, just like in here or any of your buildings on campus, you paint them. If you got metal, you paint it. So it's a similar idea where you want to paint the electrodes so they don't come in direct physical contact with the electrolyte and therefore degrade that way. And we've come up with some solutions. We haven't got the definitive solution yet, but there's still plenty of opportunity to do that.
Okay, thank you, audience. You've been very energized and engaged, and really appreciate your participation. And let's thank Professor Whittingham again.
Thank you all.